Okay, so I wanted to talk about the lab for this week. So last week we looked at measurement uncertainty. We're going to use a similar kind of setup this week. We have the carts and we have a track, but we're going to put the track on an incline. So let me draw what it's going to kind of look like. So there'll be a track, and then on the track there'll be a cart. So let's put some wheels on this thing. We'll make them into a single entity. Okay, let's put it at an angle so I can roll up this car. Okay, so there we go. So instead of using photogates this time, we're going to use what's called a motion sensor. So the motion sensor is going to be at the top of the track. And what it does is it sends out sound waves. And then the sound waves come to the cart, and then they bounce off and come back. And basically what the signal would be is they would send out a pulse, and it would be set high until the sound bounces back. So this is kind of like a signal. And what they do is they take this time that it takes for the signal to go from the motion sensor to the cart and back again. And they figure out based upon the speed of sound, they use the definition for velocity, which is velocity is delta x over delta t, or delta x is equal to v times delta t. So this t here, they'd actually take it and divide by 2 because this is actually counting the distance twice, the sound going to the cart and back again. So that they'd take half the time, they'd use the speed of sound and multiply those together, and they would get a distance. So what this motion sensor is doing is it's measuring position as a function of time. So it's going to measure this position. Now what I've done is I have measured position as a function of time, and just move the cart back and forth, and you get something like this. It's just me with my hand on the cart, moving it up closer. So closer would be down, moving it away, it would move up. So the distance is measured positive in this direction. Just away from the sensor is positive, towards the sensor is less positive. You're always going to get a positive number because it's always going to be on this side of the sensor. But as you move away, it gets more positive, and when you move towards it becomes less positive. Now what we're going to do is we are going to push the cart up the ramp, and then we're going to let it go. So part of it will be us pushing it and speeding it up to give it a certain initial velocity, and then with that initial velocity it will go up, and then it will stop, and then it will come back, and then we'll catch it, and then we'll do it again. Okay. Now, during the period where you're not touching the cart, so this is position. What we're going to do is we are going to look at velocity as a function of time. And if you do that, what you will see is that initially the velocity will be negative, and then will go to 0, and then will become positive. So this part here is up the ramp, and this part here is down the ramp, like that. And right here is 0. So when it gets to its maximum position up the ramp, it will have a 0 velocity. It'll have its minimum position. If we plotted position as a function of time, where the velocity is 0, you'll have your minimum position. And what we'll do is we will take that data and we will fit a curve to the data. So we'll end up highlighting this part of the curve, the graph, and I'll show you this in class, there's a way of fitting the data to different kinds of functions. So we will do a linear fit, because this will be pretty linear. And we'll find the slope of the curve, slope of the velocity curve is the acceleration. Now, one thing to point out also is that what we're measuring here is we're measuring position. So, you know, it sends out a signal, comes back, sends out a signal, comes back, and there's a certain what we call the sampling rate that we will have. So if you have a sampling rate of 10 hertz, say we're doing a sampling rate of 10 hertz, that means we take a sample every 0.1 seconds. So 10 samples per second. That's what hertz means. Hertz means actually cycles per second, but from a sampling rate, we're going to end up using 25 hertz just to get more data points. So what you do is you measure the position as a function of time, and then to calculate the velocity, you take the position at 2 times. So you could take it at these 2 times, you know, the initial time and the second time, and that would give you a delta x. And then there would be associated time, which would be 1/10 of a second. For this sampling rate, it would be 1/10 of a second. And so we just take the delta x divided by delta t, and that gives a velocity. So let's write this out. Position is measured. Velocity is calculated. Velocity equals delta x over delta t. Now, you can also plot acceleration. We're not going to do that because I'll tell you in a second why. So acceleration is calculated as well. So the acceleration is the change in velocity, which is divided by the change in time. So once we calculate the velocity at given times, we can then take that change in velocity between 2 times and divide by the time. What you tend to see is that the further away from actual measurements the less accurate the calculation. So the velocity is the first step away from measuring position. So what you may see if you take data, here's position as a function of time, you know, it may look like, oh, I have a nice continuous smooth curve. Then when you calculate the velocity as a function of time, like this, you might end up with the velocity going kind of like this. I'm not trying to match exactly. I'm just trying to kind of demonstrate. And then the acceleration as a function of time would then look something like, you know, it gets worse. So if I were to then calculate the next thing, which is called, what the heck is it called? It's called the jerk. So if you take the derivative of the acceleration with respect to time, then that one's even going to be more scattered, more inaccurate. So what I'm doing here when I'm using the slope of the velocity as a function of time curve, I'm really kind of averaging things out. So when I take the slope of this line, it's giving a reasonably accurate value over that time period. If you look at a value at a particular time, it may be slightly more error than I'm willing to accept. So that's why we're, instead of using the acceleration curve that's generated to calculate the acceleration, I'm going to take the velocity curve, take a slope of that, which is kind of like averaging, and that'll give me a better number, a better representative number of what is actually happening. You'll find out that this curve, velocity versus time curve, actually is pretty straight. So it's surprising, but if you do look at the acceleration versus time curve, it will start to get a little bit less accurate. And it's always easier to see these cases, these parts where you let go of the cart and it goes up by itself and comes back down. It's easy to pick those up. When they're happening on this curve, if you try to do it using acceleration, then it's harder to pick out where it starts and where it ends. Okay, the last thing is that we're going to do this experiment 10 times. So you'll push it up the ramp, come back down. The person on the computer will do a curve fit of the data, figure out what the slope is. You'll write, the person who's pushing the cart will write that number down. So the person who's pushing the cart, that's their data. And then you'll switch and you do the same thing. Now, just to make it a little more interesting, everybody's going to have 3 carts. So we're going to do it with 1 cart, then we'll do it with the 2nd cart, and we'll do it with the 3rd cart. And we'll compare, see if different carts give us different numbers, because there could be more friction associated with 1 cart than another cart. So we'll do a statistical analysis of comparing the different carts. We're only going to take 10 measurements per cart, just because doing more than that we wouldn't have enough time to do it. Now finally, we are going to measure the angle of this ramp, because we'll find out later that the acceleration due to gravity, the acceleration of something you just drop, is related to the angle of this ramp and the actually just the angle of the ramp. So it turns out the acceleration of the cart is going to end up being the acceleration due to gravity, the 9.81 meters per second squared, times the sine of the angle theta. So we're going to measure this, we're going to measure that, so we should be able to calculate or estimate the acceleration due to gravity by taking our measurements and dividing by the sine of the angle theta. There are going to be 2 ways of measuring theta. One, we have what's called an angle indicator, and you'll see it when we do it. The second way is you're going to measure along the ramp 1 meter, and then you're going to measure the height of the ramp above the table, and this is the angle theta. So the sine of theta is going to be equal to the opposite over the hypotenuse. So so we can then calculate the theta. Theta is going to be the inverse sine of h in meters. So we'll do that so that we can compare the angle measurement from geometry versus the angle measurement from using this angle indicator. And that's all.